start. So last time we introduced this notation. Let me write it again. The notation was for u tilde u bar, and it said given if fixed x, so x was the problem instance and the sequence of unitaries, u tilde is u tilde n, right? So these are the ones that we estimated. The algorithm was estimating itself, right? D was supposed to be some log log in the dimension. Yeah, so when you exponentiate it, it stays polynomial, and then these were the remaining ones, so from d plus 1 to p of x, right? So given the sequence f of u tilde u bar, we defined it as finding the best witness and writing on the probability w bar c x u bar psi. So this thing I'm putting 1. Right. Is this okay? This is the notation we had last time. So w, remember, was the description, right? Which would take. So we had written the notation was slightly different. I wrote it like this earlier instead of here. So this I had written over here. But otherwise, the point was that you hard code x and u bar into the verifier, right? And then it runs on some. It runs on some witness, and for the remaining queries to u bar, it uses. Oh, sorry, this is u tilde. I think I wrote it wrong that day as well. U tilde. And for the remaining queries, it uses u bar. Right? That was the. Is this ringing a bell? Are you with me? Yes. No. If you don't remember, I can review a little. So, okay, I don't think people seem very comfortable. So let me review the. Yeah. So that we did a little later. So then we argued that if you take the expectation of f, okay, so these were the two notes. So the probability that a outputs 1. If and only if expectation of u bar from this distribution, if u tilde u bar is strictly greater than half, right? Because that's how we had defined a. A was supposed to make those do the estimates for u tilde, then create this description and then query the language to get the answer, right? And that's exactly this object, right? And it was outputting 1 if because the language C had this inbuilt, right? The language C itself said that if this outputs. Is that okay? Does it make sense? Okay, so let's move on then. Oh, okay. All right. So now what we're going to do is we're going to also observe that the QMA acceptance probability. I suppose I also mentioned this last time. Maybe not. So the QMA acceptance probability of V itself, okay, would be FU, which is just. So remember, U bar is. It was sampled independently, right? So the problem was relative to U and C, right? That's the way the problem was defined. And so if you have the verifier for the original QMA problem, right, then one can write it in this notation as follows. So it would be max psi probability verifier UC x psi. Set accepts. Right, because remember W was essentially the same as the original verifier, except that we changed the oracle calls, right? Everything else was the same. And now what we're doing is we're giving it exactly the, so U tilde has been replaced by the actual U, and U bar has also been replaced by the actual U. So it's nothing but just running V and getting the answer, right? Is this notation okay? All right, so let's move on. Shoot, there were equation numbers which I should add. So this one is labeled equation 2, this one's labeled equation 3. And our goal now is to show that, okay, so the story is, or rather story / goal, is to show that equation 2 is a good estimator for equation 3, right? Because A is the construction that we just did, right? And if we can somehow get this, right, we know that we kind of assumed that it spread, right, the bound, because there was like a gap, and we assumed that this 11 by 12 and 1 by 12, right, there was like this weird number. So we assumed that, and then now what we want to do is we want to argue that these two, this is a good estimator for that, because it's in terms of the bound, right, that you can distinguish them. Okay, so we do this in 2 steps. Okay, the first one is we replace. It's very funny the way it's written in the paper, because okay, so let me write it and you'll see. So replace U in F's second argument with average over U bar. So it's saying you replace the second argument with an average, okay, and then the second step is argue similarly, and oh shoot, I forgot, you do this replacement, and what does it mean? It means that approximately this replacement preserves the QMA acceptance probability, right? Basically, these two things are the same, and then you argue similarly, and when replacing U by its estimate, U tilde in F's first argument. Okay, so it's nothing much, it's just saying that we'll replace this and this by the corresponding quantities, so nothing very big. All right, so by lemma 29, F is Px Lipschitz with respect to the second argument. Okay. U bar viewed as the direct sum, right? So U bar is n goes from d plus 1 to size of x in polynomial, and un, right? So what was lemma 29? I forgot. So let's see. Lemma 29 said, right, so lemma 29 is the statement that, oi, I see, you okay? Allergies. Okay. So lemma 29 says what? It says that it was a statement about VU psi. So you view it as a a quantum algorithm making T queries. Okay, and then you define FU as max over psi on this, okay, and the probability that this outputs 1. I'm just reminding you what the lemma was saying. Okay, so we proved this last time by these maxes and so on, which we had some discussion around it. So you have this v, you give it psi, you take the max, define this to be fu, okay, and the claim was that okay, and this is a quantum algorithm making at most t queries. Then the lemma said that f is t Lipschitz. Okay, so now what is being noted is that the second argument here, right, the second argument of f, which was u bar, if you fix u tilde, right, you can view it as an instance of this, right, because it's some verifier with whatever hard-coded things, and then it has the Lipschitz property relative to the unitary, right? This is fine. Okay, in the Frobenius norm. All right, so this is fine. Okay, the second note is that we're going to use theorem 10 with capital N equals 3, 4, 5, 6 mod x p mod x whole square plus 2, capital L as p of x, and little t as 1 by 12. Okay, so theorem 10, I suppose, is the it's the one where we were using the Lipschitz property. Let me see if I can pull it out for you. We did it in the beginning, I think. Or is it later? Wait. Okay. Theorem 10 is. So we use that also in the deterministic scheme thing, right? Impossibility of deterministic schemes. So the statement was as follows, right? If you have, well, this is Lipschitz, yeah. So the statement was that if you're far from the average, so if f of u, so f is, say, what is it notation? Is L Lipschitz. Okay, so this is saying if f is L Lipschitz, then the probability you sample u from the Haar measure. Okay, so it's using the concentration property of Haar measure, right? And the probability you're going to be far from the average by an amount t is going to drop exponentially. So it's going to be at most exponential of minus n minus 2 t square by 24 L square. Okay, and that is the okay, so hopefully we don't need it again. So it's clear that we can apply the lemma, right, because we know that L is P, right, because these are the number of queries you're making. And this lemma was saying that if you're making T queries, then it's T Lipschitz, right? So we know that it's P Lipschitz, and this theorem is expecting L Lipschitz, right? So this is fine. And capital N and little t. So little t is how far you are. What was capital N? Is it something you can choose arbitrarily? No, it should appear somewhere. What is capital N? Is it the size of the Hilbert space or something? Yeah, it's dimension of the domain. Yes, exactly. So this is, so n was the dimension on which the unitaries act. So these belong to un. Okay, so n is the dimension, and okay, good. That makes sense. So the dimension for us is what? So this is, we had taken log of this, right, as the, so the dimension would be 2 to the log, and this was the exact number we had used. Okay. All right. So if you plug it in, what you get is that if you sample from the distribution D, right? Distribution D was oh, sorry. Also, I forgot this. This unitary was, this mu was defined to be the direct sum, right? Of in the theorem, we not only had u, but this was yeah, it was like a direct sum of many u's, right? So it's the same thing here, right? It's a direct sum of, so that's why D is, it's not just the Haar measure, it's a direct sum of many unitaries from the Haar measure. That's all I'm trying to emphasize. Okay. So when you plug this in, minus expectation bar from T, okay, fu u bar, this mod, oh shoot, I just have to increase the size, okay, is greater than 1 by 12 with at most 2 e to the minus n minus 2 t square by 24L, right? This is just the statement of the theorem, and then you do the substitutions and you will get 3, 4, 5, 6 mod x times p mod x square by 144 divided by 24p mod x square. Okay.
What is left hand side exactly? So you wrote
This?
F, I mean,
It's just the same, right? It's just saying how far you are from the average.
no, the argument inside. So F was Lipschitz constant. Sorry, yeah, F was Lipschitz with respect to second argument u bar.
Yes.
So the probability must be on u. Oh, that is u bar, right? That you wrote u from t.
Oh, yeah. I think I messed up the notation. I see what you're saying. Yeah, this probably should be u bar for both cases. I think then it's okay. No, but it was fine. The notation was it okay? Maybe there should be a u tilde somewhere.
And the probability must be over u bar.
Yeah. No, you're right. Well, let me check. I think because the first argument should stay the same, right? Otherwise,
Exactly.
it doesn't work. Thank you for spotting that. Let me check if it's something non-trivial or I just miswrote the statement. Let's see. What did I do? Yeah, there's a u tilde. Oh no, it writes u directly actually. Let's see why that is.
Well, they must not be the same. That is my trouble.
Yeah, I agree. Okay, so for the moment, let's just write primes, okay, and then we'll see if this is enough to do the proof. This is fine, right? Yeah. In the paper, they write u.
When both are same, then you will average over.
Yeah. Then it's not correct because you had to also average properly. Yeah. So let's just write u prime and see, okay, and then hopefully. Okay, so this is fine. All right. Okay, and so this is why this number appears 3, 4, 5, 6, whatever, because they use t to be 1 by 12, and when you multiply these guys, 144, 24, this will cancel completely. Yeah. Oh no, sorry. This is u, and this is u bar.
These are dummy in this assignment.
Yeah. It's just the matching is like this part. Like these are different. That's all is important. Okay. So in the paper they've written u prime to be the same as u, which is a little bit problematic, right? Because the statement, the theorem doesn't quite say that. So I've put it as prime for now. We'll see if the proof goes through. If it doesn't, then hopefully there's a simple fix. Otherwise, yeah, you guys can make a name for yourself by fixing it. All right. So that's the.
So this is statement anyway true for all u prime.
Sorry, let me say one last thing. Yeah, exactly. It's true for arbitrary u prime. And this factor of 2 appears because the theorem was like one-sided error. So if you do both sides, you have to put you do a union bound and you'll get, okay? Alrighty. So this is fine.
So since this is true for all u prime, it must be true for fixed u as well. Different than this distribution, just like the arbitrary.
Yeah, maybe it's a special case. Like you can take u prime to be arbitrary, and in particular, I can take u prime to also be sampled from u, and it should be okay. Maybe I read it. Yeah.
Not I mean, u prime is fixed.
No, but I can also take, like, it's true for every u prime. So even if u prime happens to be identical, it's fine. Like if all I'm saying is if like say some function f a equals f b, or sorry g b. Sorry, GA, right? Then this will also be true if I take expectation of A from some distribution A, right? So since we know it's true for all u prime, you can in particular take. But I'm not so sure because.
Let's try to separate from the average. So after
Yeah, so I can probably take like a different D and put u prime. Then it's okay, but if it's the same u, then I'm a little bit concerned. So I'm not fully sure it's true. But let's see how it's being used in the proof. I hope there's nothing wrong because yeah, let's see. Let's make progress and see, because he has to connect it to the this case where the u's are the same. So if you're not able to make the link, then it might be a bit problematic. Or maybe it is true and I just don't see the argument, right? Because we don't have a counterexample. So let's see. I'll clarify it next time. Let's look at the remaining steps, at least. So, all right. So what we've established is that if you're more than 1 by 12 away, then that probability drops exponentially. Okay, so that was the second note. Now let's look at the next one. All right, so the third thing is the following. So it says, because W calls u bar at most px times, and am I messing up something? Wait, no, it's fine. Okay. And because the diamond distance between unitary channels is preserved. Don't use here, let's use the space. Is preserved. Undertaking inverses. Fact 7 implies that. So let's recall fact 7 because I don't remember. Okay, so fact 7 says, so for unitaries it says that, fact 7 says for trace for quantum channels, so trace distance between A row and B row. This is very straightforward, right? Like this is essentially just from the definition of the diamond norm, right? So any specific procedure for measuring would obviously be at most the value of the diamond norm. Right, because you cannot distinguish better the processes by.
That is taking inverses.
Oh, so if you have A, B, and you had the distance between A, B and A dagger, B dagger, essentially in that sense, it's going to be the same. Okay, so fact 7 implies that for any psi, we have probability 1 u bar c x u tilde psi, okay, minus probability 1 w u bar c x u psi. This norm is at most px by 2 u tilde n, the unitary channel that we had, u n. Okay, so I think there was a statement, right, like you're using subadditivity of the diamond norm and you're querying it at most these many times. So okay, I'm just a bit confused about the factor of 2, but I'm not fully sure how to account for that. Oh, okay. So the factor of 2 is coming because there's a relation between fidelity. Is it coming from there? Oh, I think it's just coming from here. Sorry, got confused. Sorry.
What does it mean by hard coded in the second case?
Oh, sorry. There's a tilde.
What is it?
There should be a tilde.
And what is the difference?
Oh, did I mess up? Maybe I messed up. No, that is the difference. You're right. No, it's fine. I think that's what he's trying to argue, that the difference between the estimate and the actual thing, you'll get a diamond norm for that, and then he knows the bound on this because yeah.
So hard-coded thing, do I think that as like some gate during the like procedure W, or
Yeah, I think the way to think about it is that so when you define W x u tilde, you're right, we said that we have to think of it as hard-coded, and now if u is some arbitrary thing, it's not clear, you'll have an efficient description and all of that. But I suppose even if it is arbitrary, you can have an efficient description, right, because the size of u is no, it's not true actually, because the estimate was done on
so you ignored some actual things and you estimated only efficient persons. Right, you perform process tomography on certain input sizes.
Yeah, I'm just trying to see if you're using because process tomography will only give you an estimate, but even the exact description should be efficient, I was thinking, because the size is only log many qubits. Although but in any case, I don't think it actually matters too much, because what you want to show is that you have like what you were saying, the same construction, except instead of the explicit description, you replace it with the actual gate.
Yeah, I was asking even simpler question. I was trying to think that when you say hard-coded, so how does it look like in circuit mode? So because W I will think of as a composition of different unitaries, and if something is hard-coded, then it's like
Yeah, so you basically, like you have C naughts or whatever, you have like an explicit description of U. Right? This U tilde would be like, I don't know, some C naughts or whatever. So that's what it means.
I'm saying that when will I use that? It's not clear, right? This hard-coded information,
When will you use it? Like, yeah, so wherever there was in the original verifier, so suppose the original verifier had some circuit, right? Suppose it was applying U1, maybe U1 is not a good word, or whatever.
Oh, I see. Whenever you are using U, I will put U.
Yeah, so whenever U was, the first, there's many U's, right? So the first, what was it? D, right? Yeah, so the first D will be replaced by an actual circuit instead of the oracle call, and the remaining ones are going to be, UD plus 1 and so on are going to be.
No test is misleading because I will think that, this hard coded.
Yeah. So instead of doing the hard coding, you basically replace it with the actual U, and you look at the output of the verifier, and then you try to bound the probability of getting one, the difference of the probability of getting one.
And this is for the argument's sake. You are not doing actually.
Yeah. You're just using security, right? Trying to prove security. So the important thing is that the reduction itself should be efficient, and now you're just trying to show, like, you're showing inequalities, right? So there it's okay. Yeah. Okay, so that is fine. Any more questions? Is it okay? All right. And then the fourth note is that U tilde U bar minus F U bar is going to be okay, so we made U bar the same, and now we are trying to substitute U by U tilde. So if you do that, maximum psi probability
Why is this U so much?
just a second. Yeah, let me just finish writing this and then I'll look at what you're saying. So what were you saying?
So in left hand side, U and U tilde, they are like various directions, right? Of arbitrary sizes.
Yeah, so these are sequences. U tilde was, I think, until D, and
But
U
it was a
bar
sequence.
was. Huh? Yeah.
And similarly, U was also a sequence. Then why U is appearing on right hand side? Is there a summation or somehow P mod X takes care of it?
So mod X is the instance size, I guess.
Yeah.
But you're making P many queries, so it should. Yeah, that is a good question. I think I did not notice the n. Why did I not notice the n?
I think that is a specific unitary. This U tilde and a unitary matrix.
Yeah. Yeah, that is a good point, actually. Let me see if they say anything in the paper, or if I messed up somehow. Yeah, so the way I had understood was You have a sequence. I think it's probably appearing because for a given problem size, you were supposed to access the unitary in that sequence, right? So I think this has probably more to do with how we formalized the. I think I sort of forgot how the game was formalized. So yeah, so I think this is nothing very deep, right? I think it's just saying that. So the verifier, right? I think the way we define QMA, right? Like the way we define the classes was as follows, right? So there's a sequence of oracles, whatever. Right? There was so let's call it I, or let's just call it n actually, right? N in natural numbers, and then on instances of size x, size x's, you get access to oracle O sub n, right? I think that's how we had defined it. So it's not saying anything very deep. It's just saying that because you by assumption are running it on.
So mod x is n.
Yeah, mod x is the length of the thing.
Okay, so I thought that this is some random element of the sequence.
No.
So I was wondering how to choose it.
No. Mod x is just the instance size. Okay. Yeah, sorry. It's just there's a lot of notation, so one tends to get a bit confused. But thank you for spotting the gap. Okay, good. So getting back to the statement that I was trying to write. So now we have fu tilde and u bar, and then fu and u bar, and we can just use the definition, right, and expand this, and the definition just says this. So this, so far it's okay. And now this is something very similar to what we saw last time, but just written for just written for the case of these differences. So now this essentially becomes the same as like basically you can pull out the max over psi. Okay. So individually maximizing this, right? So it could be that this one has, say, psi prime as the maximizer, and this might have phi prime or whatever. Let's call it psi prime and psi double prime as the maximizers, right? But the claim is that you're maximizing this quantity separately and this quantity separately. But if you try to maximize the difference, you can find one psi for both that would give you the max difference. Yeah, and this we got the same way we argued last time, right? Like you can take differences and argue that the one way or the other it would have to be, like whether this is greater than 0 or less than 0. That would mean that you're subtracting some big object here because it was the maximizer, and then if you choose any other element, it would subtract something smaller, and so therefore you would have. So this we did, exact argument we did last time, so I'll not repeat it. And so that would give you what? It would give you u tilde n dagger minus u n dot u n dagger diamond distance by using essentially this, right? So you can maximize over psi, and then this will still be bounded because the diamond norm bounds the best process you have for. Okay. So you get this, and then we already remember, right, that so we had an estimate. So this part. So recall the estimate satisfies this object is at most 1 by 6 2. Okay.
This was assumption, right?
Yeah, with probability at least 2/3 over randomness of Right, so U tilde was defined yeah, so U tilde we estimated, right, using the algorithm.
Oh, they are related, so this is proven then.
Yeah. The only thing that worries me a little is that we were using the n that we were using was log of something, right? It was not true in general. Right. Because, right, U tilde was supposed to be the estimate for the first D entries, right?
Yeah.
And here he's writing the entire thing. So I'm a little bit confused with the notation. Because, you know, U tilde he had defined as, like when he was defining it earlier, he had defined U tilde to be U tilde on n, where n was at most D. And D itself was bounded. So I'm a little bit.
Other part we will replace it by U bar, right?
The other part, no, those were the remaining queries. The remaining queries will be replaced by U bar, that is true. But he's writing it in terms of the diamond norm between the n sized. So that's the part that I'm a little bit confused about.
It's all the same logic, right? So you can access UN because it's the instance size.
No, but you cannot estimate a unitary acting on an n qubit system, right? Because that would be 2 to the n.
Right.
So even if your instance size is n, you can only estimate log sized estimates on this. Okay, so maybe the point is that here n maybe only goes up to D, so it's okay.
You said recall, so this means you have written previously this statement, right?
No, recall, the statement was just that this difference was, I think for n equals D, we essentially said that you can estimate it by process tomography, right? Obviously with exponential size you cannot estimate it with process tomography. So yeah, let me quickly check what we said about the estimate. Construction of the oracle. Give me a second. So here's the BQP algorithm. I'm just looking at the algorithm that we had. So it said that yeah, okay, so I think the way we have to think about it probably is that yeah, so what he's written is that, so the statement more precisely was that for each n, okay, so this estimate is, is bounded by this object for each n in D. Okay. So we know this bound for each n in D. which means that my answer to your question was earlier was maybe incorrect, which I'm a bit concerned about now, because whether n is a free variable or if it's the size of the input that is seemingly making a difference, right? Because if n was the size of the input, then we don't have an estimate, and if n is arbitrary, then okay. Yeah, let's see. So there seem to be more gaps in the proof then. Okay. Okay. Yeah, but thank you for pointing it out. I hadn't paid attention to this. Okay, so let's see if we really need to use. Yeah, whether it suffices to just take n equals d in this setting. Yeah, I think it probably does, because W's are not accessing it anyway, right? Beyond.
Yeah. Anyway, you are not proving that statement, so.
Huh? What do you mean?
I mean.
I think it's actually okay. I think it's fine, because these W's are only going to access, by construction, they will only access U's. Yeah, the only places where you were making this replacement with U tilde, right, was when the unitaries were small enough.
Yeah.
So it doesn't really matter what the rest of the unitaries are, because those will be queried at U bar. They will not be queried at using this the subscript ones.
Yeah.
So therefore, I think it suffices to assume that n is at most d. So I don't think this was true then. I think here you just have to take n is at most d, and then it's fine.
And then this P mod x is coming in front because you were querying. Yeah, exactly. This is still bothersome. So at different queries, you will query from the different sequence of unitary, right?
Yeah, but you're not querying from anything bigger. So this is just saying that even if you.
I'm just asking now that what is this n? Is the largest d or the smallest d, or what is this d? What is this n?
Is the largest d? No. Oh, which value of n you're taking? Yeah, I suppose. That is.
Because your circuit will be different at multiple places at all the queries.
Yeah. So the unitaries that you're using are going to be different. That is true. So it's going to be.
If you sum till n equal to 1 to d,
Yeah, I think maybe then it's okay.
but probably because of summation, this P mod x is coming, so everything is fine anyway.
No, I think P mod x is the number of total queries. Here.
And each query will involve one such difference.
Yeah, but each query could be to anyone from U1 to UD. That's the point.
Yeah, so you will have summation.
Yeah, so probably there should be a factor of d, I think, maybe.
No, I think because of px it will be okay. You must.
No, but the first one, so you might get things like this, right? You might get
you get
U1
U1
dagger,
Yeah.
then you might have U2 dagger,
yeah.
and so on.
So those
But
will
that
be
doesn't
P
mean.
mod x in number. All such term will be P mod x in number.
That is correct, but the bound on each one of them, yeah, actually I think in the end it will probably work out.
Yes.
But because for the bound for each one of them is the same, 1 by 6p.
Exactly.
So it's okay, yeah. But I think in the intermediate steps are a little bit messy. Okay, so if in case, I guess you guys maybe got lost or not, I don't know. But yeah, so the concern really was that, yeah, it looks like at each query you would probably have to put this bound, and as you increase the number of queries, you would likely have to allow for larger unitaries.
Yeah, definitely. It's true because your define the circuit in such a way that you define for 1 bit, then 2 bit, and then so on?
Oh man, I think I'm messing up something very basic today. Because I think what I'm not actually very clear about is yeah, my main concern is that I thought the way we defined the complexity classes was that if you're given a problem of size x, well, that is what it's doing, right? It's trying to answer problems of smaller sizes recursively internally, potentially. And when it does that, it's going to use the smaller use. Okay, it's fine. Okay. So yeah, so there's some clarification that is needed, because what can happen is that because you have a bigger instance size, right, you can query the oracle for the smaller instance sizes, right? So at any given point, you could have potentially accessed any of the smaller oracles. So it's not clear that it's enough to bound only the largest oracle. So you probably have to bound each one of them. But the point is that the bound for all of them is the same, because it's 1 by 6 poly. So it doesn't really matter in the end. But this statement, I think, is strictly probably not quite correct. So one has to be a little more careful to derive the bound. Because at the end of it, what we want is that this difference is at most 1 by 6p size of x. And I think that statement will probably still be true, even if the intermediate steps are a little shaky because of the fact that you can access smaller oracles even if you're on a bigger instance size. Because remember, right, we were trying to solve smaller instances in building using C to answer the instances of bigger sizes. Okay, sorry, that was not very clear in my head, and there was a little bit of a gap in the paper itself. So, also it seems, could be wrong, but it seems that way.
Somehow their things work out.
Yeah, but I think the argument, the conclusion is okay, which is, it's just probably needs to be written slightly properly. I think, yeah. Okay, so far so good. And then by Jensen's inequality, one gets the following. Minus expectation is at most wait, what did I do? Did I miss a step? I think I missed one step, sorry. Before we could use what is happening today? What am I messing up now? No, so the bound is fine actually. This part is fine. The quantity that we wanted to bound was slightly different because here we still don't have average over u bar, right? Because remember the actual procedure would average over u bar. So I forgot to do that step before giving you the full inequality. So now that's what he's saying is you can use Jensen's inequality to get the expectations inside, and then you'll still have 1 by 6p size of x. Okay. With probability at least 2/3 over the randomness of right, because A is the algorithm that was constructing the estimates, and this is the probability with which it gets.
But expectation will not go inside modulus,
it's linear, right? Once you have it.
If there was no modulus, then it's okay.
Couldn't you run the argument both ways? Assuming one is greater than the other and the other is greater than. Okay, this part I did not work out myself, so I don't. Yeah, I'm not fully sure if it breaks because of the absolute value. Because I suppose Jensen's inequality only works for convex or concave depending on which one. So then I had to prove that this is convex, and then I didn't want to worry too much.
Oh yeah, probably they use that fact as well.
So yeah, I don't know. But yeah, let's continue and we can sort it later, that specific inequality. Okay, so u tilde n satisfy. Okay, so these estimates u tilde n satisfy u tilde n dagger minus un dagger. Oh, okay. Sorry.
Also, the first expectation is u bar half, right? Not u tilde.
Yeah, should be u bar. Thanks. Okay. And then we note that, so NB5 is that, so over probability of A, right, this object. Oh. Okay, so expectation u bar from T, fu u bar mod being greater than 1 by 12 is at least 1/3. Okay, and why is that? So okay, so for this we have to recall a few things. So we recall equation 4, which said that probability of u from T mod fu u minus expectation u bar. This is the one that we had some trouble with, so let's see if it actually goes through this time. Expectation over fu u bar mod, right, is at least 1/12. Okay, this probability is at most 1/3. Hey, what did I do? Shoot. Sorry. This is at most. Right, that was theorem 10, the concentration property of the Haar measure. Right, that's how we got this one. And then equation 2 was what? Equation 2 was that A outputs 1 if and only if expectation u bar coming from T f u tilde u bar is greater than half. Okay, I think we're very close to the end, but I'm.
We want to use triangle kind of inequality.
Yeah. Okay. So the conclusion. I'm actually not sure. Wait, give me a second. I'm not sure if I'm trying to whether this statement is proved or I'm trying to prove it. I'm not sure. So let me check if, because if that one is obvious, then I should explain why that is true. Give me a second. Hmm. Right. Yeah. That one is probably okay because.
Yeah, because I mean, you already.
No, I kind of messed up missed a step. That's what happened. There was supposed to be. Yeah. Okay. I think I just mixed up a step. So this is supposed to be at most. Did I write it down over there? So there's a px factor coming here, right? Px by 2.
2, yes.
And then this was 1 by 6 px. So the px actually cancels. I messed up.
Yes,
That's why I was a bit confused. Okay. So you would get that this is.
And there is 1 by 12.
Yeah. So you have 1 by 6 times 2. Okay. And this happens with probability 2/3. So the negation of that would happen with 1/3.
This would be strictly less than 1.
Yeah, but okay. So this much is fine. Okay. So the recall was something else. Okay. So the recall is trying to prove the actual conclusion that we want, which is that the machine does what it should be doing. So now, so these two were fine, right? This we have, this we already proved. Okay, and so then the conclusion is that except with probability 2 to the e mod x over the unitary u, if the instance is a yes instance, right, then you'll get the following. So we'll have FUU is greater than 11 by 12, right? Because for the yes instance, we kind of already amplified the verifier, right? Okay, and which would imply the probability that A U C X outputs 1 is going to be greater than 2/3. Okay. So basically, what we want is that okay, yeah, let me write the second statement and then we figure out why this is true. Okay, so this implies f of UU is at most 1 by 12, implies probability that AUCX is 0 is also 2/3. Okay, so now what we are doing is we are saying that, you know, if you look at the 11 by 12 bound, right, so suppose this is 11 by 12 on the real number line, right, what this thing is saying is that you're going to be sorry, where's the negation that we had? I thought there was a 1 by 6 somewhere. Wait. Maybe the best way to do it is so suppose you're in the in the yes instance, is it? Because you have to work out the cases, but suppose we are in this instance, okay, so FUU is at most 1 by 12, so you're here, okay, so FUU bar is at most 1 by 12, and you know that the gap between these two is going to be at most 1 by 12, so somehow you will get an interval here, size 1 by 6, okay, and you'll get this with probability 2/3. And and yeah, so we want this thing to be at least half for it to accept, and we know that the bound is yeah, okay, so yeah, let's just do it more carefully, right? So you have 1 by 12 as the bound here, and this object we know is, say, let's say it's 11 by 12, okay, and minus there's this expectation that we want, let's call this say B, okay, so we want B to be at least half, so so this mod is at most 12, right, and then all you have to do is you have to argue that this B, so you're at 11 by 12 or 1 by 12, and you have to be 1/6 around it in order to exceed this quantity, right, and then that happens with probability 2/3, so this should follow. Okay, I mean you can take cases. You can say that if B is greater than 11 by 12 or less than 11 by 12, you can whether this quantity is positive or negative. You can have 1 by 12 minus 11 by 12, and then you can work it out. So you'll get gap of 1 by 12 in one case, and in the other case also you should get something like this. Yeah, I thought I had sorted it out very clearly in my head.
Maybe you write the expression like clearly which one we are using.
Yeah, so all that we're using is, yeah, let me tell you what we're using. So we're using the fact that we want this expectation, right? We want to see when this is greater than half or not, okay? And we know these bounds, right? Because if it's a yes instance, we know that this quantity is at least 1 by 12 or whatever, 11 by 12 for a yes instance.
And this yes instance, you want this A to accept, that is this other quantity.
Yeah, so we want to prove that with what probability will this object be greater than half? So we want to argue that with at least 1/3 or or the flip of it, which would be with probability 2/3. Oh man, that's what happens when there's like a 3-day gap between when I sorted it and I didn't write it very clearly. Okay. I think I'll have to do it live. Either that or I can actually explain it next time. I think maybe that's better. It'll not waste so much time. The argument is very simple. All that you have to do is you're basically just saying the following. You're just saying that, I know that there's an inequality, right, which is this value, right? FUU is either greater than or less than some value, right? And you know that the quantity of interest, which is this, right, is going to be in some interval, right? Because that's what the mod is saying. So it's going to be in this interval with probability something. So say for example 2/3, and you find what interval it's going to be in, right? And we want it to be in some, we want it to be, say greater than half. We want it to be on that side. So you'll see that the spread is, should do the, I cannot read my own notes, I'm getting a bit confused, but the basic argument turns out to be something like this, that it's 11/12, and then you have a spread of 1/6, okay, with probability 2/3 if it's a yes instance, and so obviously it's exceeding half, so you'll accept. And for the no instance, it would be at most 1/12, okay, and then again the spread would be 1/6, which would not let it exceed half. So with probability 2/3. So in both cases, you're able to detect it. That's all it's saying. I'm just messing up the inequality. Sorry for that, but yeah. But yeah. And why I'm getting confused is because you have to, instead of taking the 1/3, you have to like take negations. You have to do it for the 2/3. You have to, because you see the way he's written it. Normally you have 2/3, 1/3, right? He's writing it as 2/3 because he's correctly deciding in both cases. So you have to take negations, and then I'm messing up the math because I'm an idiot. But that's not news. Okay, good. So what does that give us? So that basically is already very surprising, right? Because it's saying that the entire thing, this A algorithm was a BQP algorithm, right? And it's deciding the QMA instance without having the witness, right? So that's the full magic. Now the only thing I was a bit concerned about was whether we had to use this U, that this U is sampled together or not. But I think we do use the facts. I'm actually a little bit concerned. Right?
Yeah, this first except 2 to the e, 2 times e to the minus x is coming from that.
Exactly. So it's saying except with probability to the minus x, it's coming from here, and here we are using the fact that this u and this u are the same in order to. So if indeed these u's were like, if there was a u prime here, then we could not argue that for a yes instance it's.
But since I am not getting, so since u prime is arbitrary, I can put, after computing averages with respect to second argument, I can put any u I like.
After computing averages, there's no, that argument is gone, right?
No, only second argument will be gone, right? So these averages are on second argument.
Yeah, the second argument is gone, that is true, but you want to match the first argument to the second argument, but you've already averaged out the second argument. So I don't know how you can,
No,
like
second
what?
argument is average in the second part. First part will have random instance, and then you match the first argument with that random instance. So
But you're correlating the randomness, right? That doesn't seem to be.
But it's possible that.
Yeah, maybe the statement is still true. So that remains to be seen.
Directly the same thing, then you are taking average of some function with respect to some unitary, then everything will get averaged out. Doesn't matter first or second argument, right?
Yeah. No, but the statement is that this thing is true on average for everything else fixed, right? I think it's crucially assuming that everything else is fixed. The moment that everything else starts depending on your averaging procedure, I don't think the statement will hold anymore.
Then there will be trouble.
It's like, because all the high random stuff says what, right? It says A rho U Say for example, look at something very straightforward, right? Like you say that, what was your argument, that you do trace of this? No.
No, average over.
Yeah, so there's like d mu, right? And the if you do it using the Haar measure, just let me just write it as expectations, right? It's easier because so if you do this, right, for the Haar measure, then this thing is identity, right? But then you're allowed to choose. If you're saying I can choose rho myself, then I can always take rho to be u dagger u afterwards, right? If that's how you're, and then the statement is not true anymore. So you cannot have this.
All I'm saying that I can always pick u to be, sorry, rho to be u dagger u.
You cannot, right? Afterwards, you cannot have it the same u that you're using on average, because otherwise I could do something like this, right? I could just take, you know, let's say I take sigma.
Tension, yeah.
There's no tension, it's just wrong. You cannot do that.
I'm still hoping that their statement will be correct, but okay.
No, at least not the way we've written it. Because you could always choose, you know, you can define rho to be this object, but you already averaged, that's why it's identity. If you put this rho inside, you'll get sigma as the answer, not.
I agree. Yeah, that is why I asked, but then I convinced myself that it might be true.
So it looks like this, we cannot, right, kind of go here. So there seems to be a gap in the argument. Okay, hopefully it's a minor gap, but I am not sure how minor it is. And then the last step before we, oh shoot, today I ended up being super slow. 9, 10. Okay, and then the last step is what? So the last step is basically saying that it's happening with exponentially small probability. So then there's something called the Borel. So let's finish this, right? So Borel Cantelli. So this is lemma 6. It says what? It says that sum over x so you can think of x as, you know, an indicator function, so indicates whether x was decided correctly by a or not. Okay. So this expectation is strictly less than infinity. So I'll prove this in just a sec. And the lemma basically says that if this expectation is strictly less than infinity, then the probability that, so if on an average the average of this quantity is strictly less than infinity, then the probability that this thing, you know, infinitely many things happen is 0. Which means that only on finitely many instances will the algorithm fail. Okay, that cannot scale with n, so it cannot go, it cannot be unbounded. Okay, and what was this expectation? So this expectation is expectation that this would fail, right? So the expectation would be to the I, so this is the number of possible instances. And then times 2 to the e to the minus I. Okay, and then it goes from 1 to infinity. And this is just a geometric series, and you can check you get which is strictly less than infinity. Okay. So the lemma was the statement that if there's some indicator variable, 0, 1 output variable, such that the expectation is strictly less than infinity, then the number of terms, the sum over the number of terms will never exceed, will never be infinite. It will always be bounded. With probability 1, you would have. Was decided. Sorry, not correctly, incorrectly. Yeah. Sorry, I wrote it. Because this is the probability of incorrectly deciding, right? Exponentially small. So the number of events for which it would be, number of instances for which you would incorrectly decide would always be bounded with probability 1.
Number of x's.
Little x is just the instance.
How?
So for how many instances?
Finite.
Huh?
This is some finite sum.
This is some finite sum. What is the question? If
Sorry, can you repeat the statement?
oh, the statement is just saying that the algorithm fails only on finitely many instances. With probability 1, it only fails on finitely many instances. So it makes it very, very rigorous that the algorithm actually works properly. And okay, and then oh, it's the you can make it n if you want. Is the length of the instance. Okay, and then the other thing is that because there are countably many things where it disagrees, you can hard code the answers in those cases. Because it's not scaling with n, right? So wherever it disagrees, you can always construct. So suppose your algorithm A was, so if A was disagreeing on some set, you can use A to construct A prime such that on all the instances where I was doing it incorrectly, you just hard code the correct answer. Right?
And this is necessary because if it really the QMA verified, then it should not miss on those instances.
Yeah. So it has to be probability. Okay, so this essentially completes your. So and this basically in the end gives you that promise QMA you see is contained in promise BQP. Yeah. Sorry, I wanted to do both directions today, but I messed up a little bit the proof, and then also we I think stumbled upon a gap. So. Okay. So we have 3 minutes. Okay, good. So all right. Let's make some progress with the construction. Okay. But the idea was at least clear, right? Like the details, I guess, when you work out, you'll see for yourself. Except for the one that I messed up, but the idea is clear that you estimate some of them, the remaining you replace by an average, and then you have the language C that helps you evaluate some of these instances, and then it turns out that this is actually a close enough estimate for the problem. Okay. Yeah. So the other direction is almost trivial, but they try to show it for against classical advice as well. So this is the part that. I mean, to me, it looks like it's trivial because you can just use the oracle as the random unitary, right? So. This is section 5.3. Okay, so some important things here. First is that the security.
The other direction or something?
Huh?
Like, are we doing other direction or something else?
What do you mean other direction of the containment? Oh, QMA, the BQP is obviously already in QMA, right? There's nothing to do over there. So that's equal, right?
Oh, BQP is already in QMA.
We showed QMA is in BQP. That's the non-trivial thing, right? QMA is obviously in BQP. You don't use your witness. You don't use the prover at all, right? sorry. I thought you meant for the separation. What did you mean to ask? When?
No, he said it's trivial. He said.
Oh, you thought that was trivial. Okay. I thought you were saying that the pseudorandom unitary construction is trivial. That part is actually also trivial because the oracle is giving you the unitary. So it's straightforward, but you have to show it against classical advice. I actually, yeah, it seems to be trivial. Okay, maybe I'm wrong, but I think it should be fairly straightforward. But okay. And then we now show that PRUs exist. Okay, so let me just say. So we now show that PRUs exist relative to. Okay, I think it's time. I should probably stop. Maybe one small thing I'll say before stopping is that the security proof doesn't depend on C. Okay, so whatever the language is, it will the proof technique goes through. Okay. So thank you, and